Have you ever wondered how something as simple as salt could shape the climate of an entire planet? Or how the salinity of oceans on Earth might offer clues about the potential habitability of distant worlds orbiting stars light years away? Today, we're diving deep into a fascinating intersection of oceanography, climatology, and exoplanet science, a journey that will take us from the icy seas of Earth to the mysterious oceans of planets beyond our solar system. Let's start with Earth, our home, a planet whose climate is a complex, interconnected system influenced by countless variables. Among these variables, ocean salinity, essentially the concentration of salt in seawater, plays a surprisingly crucial role. It's easy to overlook the significance of something so common, but the saltiness of our oceans affects much more than just marine life. It has profound impacts on global climate patterns. This relationship between salinity and climate is not just a trivial detail. It's a fundamental aspect of how our planet functions. First, let's break down the concept of albedo. Albedo is a measure of how much sunlight a surface reflects back into space. It's expressed as a number between 0 and 1, where 0 means no reflection, total absorption, and 1 means complete reflection. The higher the albedo, the more sunlight is reflected, and the cooler the surface remains. For example, the ice-covered surface of Antarctica has a high albedo, reflecting most of the sunlight it receives, which helps keep the region cold. Conversely, darker surfaces like oceans and forests have a lower albedo, absorbing more sunlight and contributing to warming. Now, here's where ocean salinity comes into play. The salinity of seawater influences its freezing point. As the salt concentration increases, the freezing point of water drops, making it harder for sea ice to form. This means that in regions with higher salinity, less ice is likely to form, which in turn lowers the albedo because there's less ice to reflect sunlight. A lower albedo means that more sunlight is absorbed by the ocean, which leads to warming, a feedback loop that can have significant implications for global climate. But the story doesn't end there. The interplay between salinity and climate is part of a broader, dynamic system that includes ocean currents, atmospheric circulation, and even the planet's rotational dynamics. For instance, the distribution of salinity across the world's oceans is not uniform. Various factors such as evaporation, precipitation, river inflows, and ocean circulation create regions of varying salinity. The North Atlantic, for example, is one of the saltiest parts of the world's oceans due to high rates of evaporation and the influx of salty water from the Mediterranean Sea. These salinity gradients drive ocean currents, which play a crucial role in redistributing heat around the globe. The thermohaline circulation, often referred to as the global conveyor belt, is a massive, slow-moving current driven by differences in water density, which are in turn influenced by temperature, thermo, and salinity, haline. This circulation is essential for maintaining the Earth's climate by transporting warm water from the tropics to the poles and cold water back to the equator. Disruptions to this system, whether through changes in salinity or temperature, could have dramatic impacts on global climate patterns. Now let's take this concept and expand it beyond Earth. What happens when we consider exoplanets, those distant worlds orbiting stars far from our own sun? The study of exoplanets has exploded in recent years, with thousands of these planets now confirmed. As we look at these distant worlds, one of the key questions scientists are asking is whether they could be habitable. And just as on Earth, the presence and characteristics of oceans could be a major factor in determining habitability. One of the most intriguing targets in the search for habitable exoplanets are those orbiting M-dwarfs, also known as red dwarfs. M-dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They are smaller, cooler, and less luminous than our sun, which means that the habitable zone, the region around the star where conditions might be right for liquid water to exist, is much closer to the star. This proximity has profound implications for the climate and potential habitability of planets in these systems. A study led by Kyle Batra from Purdue University explores how ocean salinity might influence the climates of planets orbiting these M-dwarfs. The research uses advanced ocean atmosphere general circulation models to simulate the effects of varying salinity levels on these distant worlds. The findings are fascinating and shed new light on the potential for habitability on planets far beyond our solar system. The study reveals that planets orbiting EM dwarfs might respond differently to changes in ocean salinity compared to Earth or planets orbiting sun-like stars. On Earth, as salinity increases, less sea ice forms, which reduces albedo and leads to warming. However, the researchers found that on M-dwarf planets, the relationship between salinity and climate is more gradual. These planets do not experience the same sharp rise in surface temperature as salinity increases. This suggests that the climates on M-dwarf planets might be more stable, even as ocean salinity varies, which could be a positive indicator for habitability. But there's another twist. Many planets in the habitable zones of M-dwarfs are expected to be tidally locked, meaning one side of the planet is always facing the star, while the other side is in perpetual darkness. This creates extreme temperature gradients across the planet, with a scorching day side and a frigid night side. The dynamics of such a planet's climate are vastly different from what we experience on Earth. In a tidally locked world, the interaction between the star's radiation and the planet's surface is highly asymmetric. The day side, constantly bombarded with stellar energy, might be devoid of sea ice, especially if the oceans are saline. On the night side, however, temperatures could plummet, leading to extensive ice formation. Interestingly, in such scenarios, the sea ice on the night side wouldn't contribute to the planet's albedo in the same way it does on Earth because it's not exposed to sunlight. This decoupling of albedo from ice coverage could lead to unique and stable climate states that are difficult to predict based solely on Earth-like models. The study also explores how different levels of salinity could affect the global circulation of oceans on these exoplanets. On Earth, the thermohaline circulation is crucial for distributing heat around the planet, but on a tidally locked exoplanet, ocean currents could behave very differently. The researchers suggest that salinity-driven currents could play a significant role in redistributing heat from the day side to the night side, potentially moderating the extreme temperatures and creating a more hospitable environment for life. However, this research also highlights a significant challenge: our current inability to directly measure ocean salinity on exoplanets. While we can model these effects and make educated guesses, direct observations are still beyond our reach. For now, we rely on indirect methods, such as studying the atmospheres of exoplanets and looking for signs of water vapor or other indicators of oceans. Future missions, such as those planned by NASA and the European Space Agency, may bring us closer to directly detecting oceans and their characteristics on distant worlds. Despite these challenges, the implications of this research are profound. It suggests that ocean salinity could be a key factor in determining the habitability of exoplanets, particularly those orbiting M-dwarfs. The fact that these planets might have more stable climates, even with varying ocean salinity, increases the chances that they could support life. But this is just the beginning. The study of ocean salinity on exoplanets opens up a whole new avenue of research, one that could reshape our understanding of habitability in the universe. As we continue to explore the cosmos, we must consider the many factors that contribute to a planet's ability to support life, factors that may be very different from those on Earth. So what does this all mean for the search for life beyond our solar system? It means that we must expand our thinking and consider a wider range of possibilities. Habitable planets might not look like Earth. They might have different climates, driven by different factors, but still be capable of supporting life. The study of ocean salinity is just one piece of this puzzle, but it's an important one. As we continue to discover more exoplanets and learn more about their environments, we may one day find that the key to finding life lies in the salty depths of distant oceans. In conclusion, the exploration of ocean salinity's impact on climate, both on Earth and on distant exoplanets, is a fascinating field that blends oceanography, climatology, and planetary science. It challenges us to think beyond our own planet and consider how the fundamental processes that shape Earth's climate might operate on other worlds. The more we learn, the more we realize how interconnected and delicate the conditions for life truly are. As we continue to search the stars for signs of life, let's keep asking questions, pushing the boundaries of our knowledge, and exploring the incredible diversity of worlds that exist in our universe.